Hello, welcome to the fifth homework of the machine learning. And in this practice lab, we are doing the advice for applying machine learning. And we will explore techniques to evaluate and improve your machine learning models. And, okay, for the outline, we have first packages and secondary evaluation and learning algorithm. And third of it, bias and variance. And third of it, evaluating a learning algorithm, neural network. Fifth, model complexity. And six, regularization. And seven, iterate to find the optimal regularization value. Okay. Um, okay, here. I just run the packages for me. Am I getting any error or not? I didn't have an error. It's just run. And the evaluating a learning algorithm, polynomial regression. Let's say you have created a machine learning model and find it fits your training data very well. You're done, not quite. The goal of creating the model was to be able to predict values for new examples. And how we can test a model performance on new data before deploying it? The answer is two parts. The split or original data to training and test sets, and the user training data to fit the parameters of model, and user test data to evaluate the model on new data. Develop an error function to evaluate your model. And here, okay, we are 2.1 splitting your dataset. Lecture advice reversing to the 40 percentage of or data sets for testing that use an skip-learn function trains test split to perform the split. Double check the shapes after running the following sense. Okay, let me run this one. And we have we have images in here, bias variance. Okay, I don't want to go to here. Assignment utils. Okay, I was looking extra and just trying to here. Here's my data sets. Okay, okay, load data we have public setting here, and yeah, okay. Next, we are having the shape of our training and test shapes. We have for 18 data, and 12 of them is training, and 6 of them is test shapes. And plot train test sets. You can see below the data points that will have part of training in red intermixed with those that model is not trained on tests, and this particular data set is quadric function with no z dot. The ideal curve is shown for reference. Okay, I'm just running here the ideal here for this one, and this is our test values, and this is our training. Actually, I guess it's a good. Yeah. And error calculation for model evaluation with linear regression. We have this mathematical representation of our linear regression, and we have the exercise here, create a function to evaluate the error on data set for linear regression model. Okay, begin unit test, this one. Okay, I'm just clicking for the hint. Actually, okay, this is basically giving me the code, I guess, isn't it? Yes, actually, 48 range. Actually, yeah, it simply gives me error. Mm, okay, let me look at it. We have R for error, and okay, and it's will equal plus equal to up. I click wrong. U I is the CSU in here, which is given, and U hat is That's given for me. Minus u hat must be I. It's always adding this one. And is this was square root? Yes, this is square root, so I'll just square root it. Oh, I made it too much. And I have to add another code for myself. And it's dividing to 2m. Yes. So arrow equal divide them. And I'm just running here. What? Where did I write my code wrong? Expect and I then isn't in the same root. Oh, okay, yeah. Yes, I missed this one. Sorry. Yes, and u hat and mp array is given in here, and I'm just running this one. Okay, I'm having a wrong value expected 0. This one. Okay, I made an error, but where? I guess I forgot to in here. I guess. Let me check it. I'm not sure about. Yes, it's wrong. Let me check it. Error equal error I u hat minus 2 error. Oh, yes. Actually, I'm kind of right and I'm kind of wrong. First of all, I'm wrong in here. It must be out of this line, and it always must be calculated for each time. So I have to. I'm just gonna use this code. I'm taking for, isn't it? Yes. Was it here? Yes. Okay. Actually, what did I make wrong? It always have to be calculated one of them, then adding for error for every error I, and I have to divide it too. I forgot first of all. Then I remember that I made a wrong in here. So let's just pass it and compare performance on training and test data. Let's build a high degree polynomial model to minimize training error. This will use a linear regression function from sklearn. The code is in the important utility file. If you would like to see details, the below are. Okay, create and fit the model and computer on training set and computer on data set. We're just basically calculating the error and checking the fits. Okay, we are training error is 5 and test error is what? Isn't it so high? 0.2. Okay, but what? This is just calculating the all errors. I guess it's calculating the all errors, but not dividing to percentage. And this is an example of overfitting. In here, just giving the training, cross-validation, and test percentage of or sets. For training, we are using the data users to tune model parameters V and B in training of fitting. And in cross-validation, we're using data to tune other model parameters like degree of polynomial regularization or the architectural of the neural network. And we are using the 20% of test to test a model after tuning to gauge performance on new data. And actually, it is kind of a new data for us. And let's generate three data sets below. We are also using the train test splits from learn, but we will call it twice to get the splits. Okay, just dividing it to three splits, like training, cross validation, and test. And in here we have bias and variance. Above it's clear the degree of polynomial model was too high. How you can choose a good value? It turns out, as shown in the diagram, the training and cross-validation performance can provide guidance. By training a range of degree values, the training and cross-validation performance can be evaluated. As the degree becomes too large, the cross-validation performance will start to degrade relative to the training performance. Let's try this. For example, okay. Let me try to close diagnosis bias and variance. It's in here, and this is the figure. Okay, plot training, cross validation, and tests. I'm running this one, and as we can see here, this is our training set, the red ones, and cross validation for the orange, and test data is blue. And in here we're just running XU training. Right, this is the training, and CV is representing the cross validation, and test is representing test data for us, and divide it into in here as X train, XCV, and X test. We're just in dividing our tests data to sets, and we are just representing and showing the figure in here. And finding the optimal degree. In the previous labs, you find that you could create a model capable of fitting complex curves by utilizing a polynomial, and further you demonstrated that by increasing the degree of polynomial, you could create overfitting. It's actually even in here example, overfitting like example in here, kind of example, but actually yeah, shallow goes trace for all trace. Yeah, where I was. Yeah, I was here. And let's use the knowledge here to test our ability to see uh, ability to tell the difference between overfitting and underfitting. Let's train the model repeatedly, increasing the degree of polynomial each iteration. Here we are going to use a skid-learn linear regression model for speed and simplicity. Running, and let's see the pilot in here. This is actually showing us, and yeah, these are out of the blue one is over underfitting. The purples are giving me overfit till we training the sets, showing us the from underfit to overfit. The pilot above demonstrates that separating data into two groups, data the model trained on, the data the model that has not been trained on, can be used to determine if the model is underfitting or overfitting. In our example, we create a variety of models, varying from underfitting to overfitting by increasing the degree of polynomial usage. If we just increase the polynomial, and it becomes more overfit. On the left pilot, the solid lines represent the presentation from the models, as I said. A polynomial model with degree 1 produces a straight line that intersects very few data points, while the maximum degree is very close to every data point. On the right, the error on the trained data blue decreased as the model complexity increased as expected. The error of the cross-validation data decreases initially as the model starts to confirm the data, but then increases as the model starts to overfit on the training data and fails to generalize it. It's really good working on the training sets, but if we give it another data, it will not work as well as good. And tuning regularization. And in previous labs, you have utilized regularization to reduce overfitting, similar to degree. Just simplicity is better for the machine learning, and it's actually better to reduce overfitting. And similar degree, one can use the same methodology to tune regularization parameter lambda. And let's demonstrate this by starting with a high degree polynomial and varying regularization parameters. Let me. The lambda in here actually just simply to learning curve for us, kind of. Yeah. It's here. When it's zero, it's like goes like this one. When it's too high, it's actually better for us. And this is the better optimal lambda in here. This is the bottom of the line, bottom of the uh, cross validation error in here. Actually, we have the really small range of the training error. Above the pilots show that regularization increases the model moves from high variance in the overfitting and model to high bias underfitting model. The vertical line in the right pilot shows the optimal value of lambda. In this example, the polynomial degree of was set to 10 and getting more data, increasing training set size, the M, and training's as always better for us. And when a model is overfitting, collecting additional data can improve performance. We can within the extra data we can reduce the overfitting. Yeah, like this one. When it's the overfitting might be looking like this one, but we can reduce this one. The above pilots show that when a model has high variance and is overfitting, adding more example improves performance. Not the curves on the left, while the final curve with the highest value of m is a smooth curve that is the center of the data. On the right, as the number of example increases, the performance of training set and cross-validation sets converge to similar values. Not that the curve are not as smooth as one might be seen in a lecture. This is to be expected. The trend remains clear. More and more data improves generalization. Basically, this is the most important sentence in here. More data improves generalization. Basically, simply want to say this one. And evaluating a learning algorithm, neural networks. Above, you tune the expected a polynomial regression model. Here you will work a neural network model. Let's start by creating a classification dataset. And here just simply a classification. And in here, dividing 3 times training, cross validation, and test. We're just splitting this symbol and training and ideal performance in here. Above, you can see the data on the left. There are 6 clusters identified by color. Both training points and cross validation triangles are shown. In here, this is the no, it's in here. The interesting points are those that fall in ambiguous locations where either cluster might consider them members. What would you expect a neural network model to do? What will be an example of overfitting, underfitting? One of the right is examples of an ideal model, or a model that might be create knowledge of the source of data. The lines represent equal distance boundaries where the distance between center points is equal. It's worth nothing, then this model was misclassify around 8% of the total dataset. Okay, I just click here additionally. Oh, okay. It's given the formulation in here. I just misclick in here and in here the 2. Okay. Um, After the example 2, we have example 3. What happened here? And we have example 4. And after this one, we just exercise 5. Okay, we have 4 more exercise and they're coming as a row. So I'm just gonna stop recording here and I will write the exercise as a row. Then I will continue to recording and trying to explain uh, the this lab exercise. Thanks for the listening. Okay, we can continue now. It was in the exercise 2. Okay, no, I made a 2 actually. Yes, but if you want to, if I want to, I need to explain in another time. I'm just within respecting to this formula. We're just adding to here. If it is incorrect, we're just adding to +1 to evaluating our categorization for the wrong ones. And here, I just run it here and gives true. Let it pass it. Categorization error 0.33 and categorization error is 0.25 in here for the both U temperature and error when we are running it 2 times and model complexity. Okay, dense layers is given the dense layers for us, and as I said here, I can explain. Okay, let me see. Am I made a mistake in here? Okay, dense layer with 120 activation, real activation, that one, layer 1 actually, and 40 in layer 2, and linear activation and complying gas. I'm not sure about I did wrong or not. Let me actually, that there must be a hint in here. Okay, I just stopped the recording. Just stopped the running, so that's why I'm probably taking errors. I just checked this one actually. Yes, let me see. Okay, I made some errors in here, so I just want to check to hints in here. Okay, let me run this one. I'm running the 1000 deploy, so it might be taking some time actually. It's in. I guess this will take a little bit time for us. So I will continue to understanding to explain the other ones. Let me see, is this going through? We have 13 depots within the thousands. Yes, okay, it's run. Keras is already in here and begin the fit. Let me see how much it will time. It will take time. Okay, that might be taking so much time actually. It's just running and stopping. That's why we are at already 800s, 900s now. Yeah, and in the thousands in here, let me run unit time model complex. Okay, why this is giving me error? I'm not sure. Let me close the hints. Let me run this one. This is my training data and cross validation data. These are looking similar. And okay, what is I'm having the attribute error in here, begin unit test and model test in here. The model is complex. Okay, yes, as we given in here, these are the parameters of us. And we are having the layer complex has never been called, thus has defined the input. Yep, begin unit test. Okay, let me check for hints. I might be making some wrongs in here. It's actually, if I have to be writing some codes in here, must be writing the code. That's why I didn't check it. This is our model feed approach 100. Model feed approach 100 extra. Doesn't it? Okay. Mm, so is that gonna click more hints? Okay, Python random seed sequential one and model comply model dot feeds approach thousands. Actually, I want to, yeah, for this notification for this node one, I will not change this one. Probably it is not outputting so something. That's why it's giving me error. Or I am having some errors in here. Am I having some errors? No. I will not change here for the node. And I'll run it again. And this is giving me training error complexity in this one. And this model has worked very hard to capture outliers of each category. As a result, it has miscategorized some of the cross-validation data. Let's calculate the classification error. We're just, yeah. Actually, it's a good. It's looking good for me. Okay, let's try a simple model exercise for below the comparison. A two-layer model. We have dense layer 6 unit, rel activation, and 6 unit linear activation. And loss with sparse categorizer compress, remember to use from logs true, and ADAM optimizer with learning grade 0.03. It is in here, learning grade 0.003 from logos true in here, and sparse categorization for the loss, and dense layer with 6 linear, and then 6 layer with the rel activation in here. I'm just running this one. Okay, it's given me error. But why? Actually, I just simply read everything, whatever it's writing. I have to run this one. Let me check this one. Actually, must be true. Let me see what I am forgetting. Then 6 really input shape. I will just copy this one to compare what is my mistake. Where I can write it in here. I'll just call it in here. Let me put then 6 activation really. Oh, okay. I forget name L1 and then it's classes activation linear and name L2. Okay. For my error in here, I just forget. I just write input shape as none, but it must be name equal L1 and linear. Sorry, name equal L2 in here, and okay, name equal simple. Let me copy it. Actually, okay, name input 6 is here. So I'll just paste it in here. I have to delete this one. Double tabs. Yeah, this is looking good to here. Let me run this one. This gives true. I'm running the import logging to get logged the test overflow with this one. It will take, okay, like 10 seconds, 30 seconds or something like this one. I'll close these ones. And let me delete this empty page for me. After this one, I'm going for the regularization, and As in a case of polynomial regression, one of the can apply regularization to moderate the impact of more complex model. Let's try the below. And here the exercise 5. I'm just gonna explain whatever I done in here and reconstruct a complex model, but time include regularization, block compression, a three-layer model. The first of all, 120 units real activation, 120 real activation, kernel equal regularization dot font tree. Actually, I made wrong in here. Let me regularizer TensorFlow keras dot regularizers dot L to 0.5. I guess I shouldn't give input in here. Okay, one, come. Must be true now. And 40 units. Relay activation, kernel, regular razor. I'll just delete this ones. TensorFlow, keras, risers dot L2 0.1 and 6 senses linear activation in here and in here. Okay, loss with the space category goes, from through and atom optimizer with 0.3 and our matrix is accuracy. Let me check the before quote. Yeah, okay, it's run, it gives true. Okay, model simple. Actually, I guess it's true, but I'm not gonna change anything in here. It's giving me the model plotting routines file. Yeah, in here, the red ones are the outliers, brown are the outlines for us, and the simple model does pretty well. Let's calculate the classification error, like the error in the red one. It's 0.003 and 0.100. As I said, the regularization. Let me run this one. It gives true. Testing. And beginning unit test. Let me reiterate to find the optimal regularization value. As you did in linear regression, you can try many regularization values to this code and take several minutes to run. If you have time, you can run and check the results. If not, you have completed the graded parts of the assignments. And as regularization is increased, the performance of the model on training and cross-validation dataset converge. For this dataset and model, lambda, if the lambda bigger than 0.01 seems to be a reasonable choice. And this is our test and conclusions. You have become familiar with important tools to apply when evaluating your machine learning models, namely splitting data into trained and untrained sets allows you to differentiate between underfitting and overfitting. Creating three datasets, training, cross-validation, and tests allow you to train your parameters W and B with the training set, two model parameters such as complexity, regularization, and model of examples with cross-validation set evaluate your real-world performance using the test set. Comparing training versus cross-validation performance provides insight into a model's propensity towards overfitting, high variance, or underfitting, mean of high bias. Want to experiment ungraded code? Okay. I'll check it later on. Let me check this one. For here we was in the regularization part for us, the last part for the gradients and model sequential. Yeah, actually you're right there. And sequential in here. So 8 dance given the parameters for us and the output shapes. Let me run it. Okay. Training data is showing us, and looks very similar to ideal model. Let's check the classification error. These are the classification errors for us. And classification errors is getting lesser. Complex model is lesser, but I'm not remember the number of the simple models. Let me check. It's the same. Sorry, it's the same as the other one, and iteration in here. Oh, why it is looking like it stopped and restarted? I don't understand. It's not like okay. It will take a little bit time for us actually. I guess I showed the two outputs of it, but 13 approach 100. Let me see a little bit. Yeah, it will take a little bit time for us. And wh- I guess yeah, I guess I have some error with my RAM. Okay. I will stop recording in here, and after finished, I will explain a little bit, or I will show the outputs of it. Thanks for the listening. Okay, yes, it's finished my iterating to find an optimal regularization value, and it's found out lambda finishes 0.3 as, and it's in the here. And as regularization is increases, the performance of the model on the training data and cross validation data set converge the set model lambda 0. Yeah, in here, this is bigger than 0.01. So sometimes bigger learning, uh, mm, bigger steps for learning is better. And to comparing this one, this is given like this one error was 0.16, and this is 15, and this, like as you can see, this is taking the reds inside the blue, and in here it's taking a little bit blue in here for the outlines, and this is more linear displaying. And yeah, our test is small and seems to have a number of outlines, so classification error is high. As we can see in here, the performance of our optimized model is compared to ideal performance. And thanks for the listening. Have a good day.